All right, welcome back, guys and gals. Today, lesson number 10, we're going to be doing log graphs and special logs. So, as always, anytime we have a new function, we're going to talk about how to graph them and what happens when we transform them. Like we've done with exponential functions, with square root functions, with our trig functions, with all our polynomial functions, quadratics, cubics, quartics, right, etc. All right, we're going to do some transformations today on log. Nothing too crazy. But again, we're going to see they're exactly the same as they've always been. So for today's warm-up, why don't you guys just graph f of x here first, log base 5 of x. On Monday, we graph log base 2 of x. So let's see if it's any different graphing log base 5 of x. Alright, so pause the video and give that a shot. Alright, so the way I would graph log base 5 of x is I'm going to make a table and get some points. Alright, so to be honest, I am not that adept, I'm not that great with log functions. I still kind of think of it in terms of an exponential function. Right? I mean, I could tell you something like log base 5 of 25, right, equals 2. So I'm going to have the point 25 comma 2. Right? But the reason I know that is because I think of it like a what power function. What power of 5 is 25? And I know 5 squared equals 25. Right? But I wouldn't recommend plugging in values for x first. What I would do is write this in exponential form. I'm just going to make f of x y to make it easier. So in exponential form, that's 5 to the y power equals x. So this is one of those weird functions where it makes a lot more sense to plug in for y first and then to figure out the x value after, even though our x values are still technically our inputs. So I know, for example, when y is 2, right, my x value is 25. So you don't want to just plug in random values for x because, like, if you did that, normally we might try to plug in like a 0 for x first to see what that's equal to. But plugging in a 0, we're going to get log base 5 of 0 is equal to what? Or equal to y. So exponential form, we get 5 to the y power equals 0. And so 5 to what power equals 0? And yeah, you can't do that, right? Because raising a positive number to any exponent is not going to give you 0. Right? Raising it to the 0 power does not give you 0. If that's what you're thinking, that gives you 1, right? So nothing works here. If you just plug in a random value like x equals 3, well, 5 to the what power equals 3? You can't really do that. That is defined, but it's going to be it's going to be an irrational number, so that's not going to be helpful either. So it makes a lot more sense plugging in for y. So if I plug in, let's say, a 1 for y, I know my x value is 5. If I plug in a 0 for y, 5 to the 0 is 1. If I plug in a negative 1, 5 to the negative first is a fifth. 5 to the negative second is a 25th. All right, so I'm going to plot these values, and let's see what that looks like. So 1/25th, comma, negative 2. All right, that is not accurate. It should be a lot closer, but I can't get it close enough. Next, we'll have a fifth, comma, negative 1, 1, comma, 0. I think we had 5, comma, 1. And then we're going to have 25, comma, 2. So that's going to be like way out there. But connecting our points. All right, our log function is going to look something like that. So like we said, we're going to have 25, comma 2, and then we're going to have 125, comma 3, even further out, right? And then 625, comma 4. So this function does still keep increasing. It just increases really, 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 really slowly, right? And if you think about its inverse function, y equals 5 to the x, well, let me graph that real quick, right? I'm going to graph y equals 5 to the x. It's inverse. That's going to have 0, comma 1, 1, comma 5, 2, comma 25, etc. Right, so just plotting those 2 points, it's going to look something like this. So the faster your exponential function grows, the slower your log function is going to increase, right? Because they're inverse functions, right? So we know it's the reflection over y equals x, the two graphs. So for this portion, however fast this is growing, the faster that grows, the slower this part's going to be growing wise. Right? So if we compare this to log base 2 of x, which I have down here, we graph this on Monday, well, that's going to look like this in comparison. All right? So do you see how this grew a lot slower? Which means it's growing faster here for log base 2 of x. And yeah, that's all. So, that coloring probably drew people off because, yeah, I don't know why this was written in red, right? But that's going with this graph, not the red graph. So, general idea is the larger the base is for a log function, right? The larger that is, the slower it's going to increase in this section over here. All right, hopefully that made sense. And now let's just talk about some basic transformations like we always do. So f of x was log base 5 of x. All right, if I have f of x minus 3, that'll be log base 5 of x minus 3. All right, and it's good practice to put the argument, right, that's what we're taking the log of, in parentheses, just so we know it's not log base 5 of x minus 3 in parentheses like that. So let's differentiate. And I'm just going to make this y equals that. So what's going to happen when we graph this? Let me copy and paste this table. And we've seen this many times, but it's going to be nothing different, right? If we do f of x minus 3, well, all I have to do is subtract 3 from all of these values, right? They're going to be 3 smaller, right? Log base 5 of 1 was 0, so log base 5 of 1 minus 3 is going to be 0 minus 3. It's going to be negative 3, right? Minus 3 here, that's going to be negative 4, negative 5, right? We're just shifting it down 5 units. That's going to become negative 2. This will become negative 1. So if I plot those new points, right, it's a vertical shift down 3 units, copy, paste, 1, 2, 3. And let me change that to blue, and let me label my graphs. So this was our original f of x, log base 5 of x. This here is f of x minus 3, or log base 5 of x minus 3. So exactly what we expect, right? This is a shift down 3 units. So this should also be what we expect, which is, all right, hopefully you're thinking, this is a shift 4. Is that to the left or to the right? It's going to be shift 4 units left. Right, if we know anything about transformations, that's what it should be. So let's take a look. I gotta copy and paste this table again. So let's see why that is. This is f of x plus 4. So, let's see what's happening. So, I know if I go back to my original function, log base 5 of x, f of x is this, right? I know, for example, when x is 5, right, that 5 to the first power is equal to 5, right? My base raised to the exponent equals 5. So if I shift this 4 units to the left, if I still want this to equal 1, right, well, what do I need to plug in now? Well, instead of plugging in a 5, because I know when that's equal to 5, it's equal to 1, so x plus 4 now needs to equal 5, so this has to be 1 instead. right? I know when this entire thing is equal to 1, log base 5 of 1 is 0, because 5 to the 0 power is equal to 1. So when my inputs are now x plus 4, what do I need to plug in here to get 1? I need to plug in a negative 3. Right, so we're shifting 4 units to the left. If you notice, what I'm doing is I'm just subtracting 4 from all those values. Right? In order to make this 25, I need to plug in a 21 for x. Right, so 21 plus 4 is 25. Log base 5 of 21 plus 4 is 2. So I'm subtracting 4 from all my values. What's a fifth minus 4? 1/5 minus 4. I guess I make that into 20ths, negative 19. No, that doesn't make sense. All right, that does make sense. Negative 19/4. And what is a 25th minus 4? I think that's negative 99/25. All right, doesn't really matter. But when we graph this, right, that's going to be a shift left 4 units. So copy, paste. So hopefully that's not unexpected. I'm using this point 1, 0 to orient myself. So 1, 2, 3, 4. That's a shift left 4 units. So the interesting thing I want to point out here is when we shifted it left 4 units, our vertical asymptote, right, also got shifted 4 units to the left. Right, the original vertical asymptote is the y-axis, x equals 0. Right, but once we shift it left 4 units, our vertical asymptote also gets shifted left 4 units, and that's going to be x equals 4 now. So the domain of this guy is, x equals negative 4. The domain of this guy is x values greater than negative 4. All right, we're not going to graph all of them. Just want to give you the general idea. 2f of x. F of x again was log base 5 of x. So if I do 2 times that, that'll be 2 log base 5 of x. Y equals. If I copy this table again, right, when I multiply by 2, that's a vertical stretch. All my values are going to multiply by 2, right, into y. All my y values can multiply by 2, right, 2f of x. So that becomes negative 4, negative 2. I gotta go back and look. 0, 2, and 4. So when we graph this one, it's just going to be, well, let's plot these points actually. I'm just going to plot 1, 0, 5, 2. It's getting kind of messy, right? But hopefully you guys see it. It's a vertical stretch, right, compared to the original. All right, it's too messy. There's too much stuff, but right, it's growing faster. It got all its y values got multiplied by 2. All right, when we do f of 2x, well, now we're changing the inputs. It's log base 5 of 2x. All right, for this, probably helps. We didn't really do too much of this, but this is going to be a horizontal kind of transformation. We did it with trig functions. So remember y equals sine x. Right, when we graph y equals sine of 2x, right, that was a frequency transformation, as you all know. Well, maybe you used to know. I'm thinking a lot of people forgot how to graph trig functions. But anyway, all right, y equals sine x looks like that from 0 to 2 pi. Remember when we graph sine of x looks like that from 0 to 2 pi. When we graph y equals sine of 2x, right, that's going to be twice as frequent. That looks something like this. So this is a horizontal compression. It's going to be squeezed together horizontally. This is a horizontal compression. All right, you don't really need to know too much more than that. But if I paste the table, again, we have log base 5 of 2x. This is now f of 2x. So again, if I plugged in a 5, this would become a 10 now, right? So in the original, I knew that log base 5 of 5, right, was equal to 1. Well, what do we need for the input now here for this to equal 5? Well, we need it to be 2.5. It has to be half the value. So this becomes 2.5. We know log base 5 of 25 is equal to 2. So what do we need in this input now for it to be 25? Well, we need half of 25, right, or 12.5. Right, so instead of 1 comma 0, this will become a half comma 0. Instead of 1 comma 5, or 1 over 5, that becomes 1 over 10. That becomes 1 over 50. Right, so we're having all the x values when that happens. And that's going to be a horizontal compression. Right, if you want to plot those points, go ahead. But what's going to happen to our original graph, right, this guy, is it's going to get pinched in. It's going to squeeze in, right? And imagine those two arrows like pushing in the function. That's what's happening when we multiply by 2, right? And the bigger number we multiply by, the more it gets squeezed in. And when that number is less than 1, right, that'll be a horizontal stretch. Right, like the x and y transformations are all opposites, if that makes any sense. So, and actually, I think we've done enough of these transformations. I'll just talk really quickly about E. You might think this is a shift left 2 units, but if you guys remember from what we did in trig, you need to factor out first. So there's really f of 2 times x plus 1, right? And it's actually just going to be a shift left 1 with a horizontal compression factor of 2. All right, so that's all I'm going to say about that. So transformations for log graphs, as you can see, hopefully, it's consistent with everything else, right? It's just a little weird because we're not familiar with log graphs yet, or log functions in general, but everything stays the same, right? All the transformations work the same way. So down here, give this one a shot too. Which of the following equations describes the graph below? Show all work or explain how you made your choice. All right, so for any log graph, I know it's going to pass through the point 1 comma 0 if there are no transformations. For any log function, it's always going to pass through the point 1 comma 0. So let's just take a look at like log base 2 of x, for example, or y equals log base 2 of x. In exponential form, that's 2 to the y is equal to x, right? So when my y value is 0, right, no matter what my base is, the x value is going to equal 1. So I will have the point 1 comma 0, right? When y was 0, x was 1. So that's 1 comma 0. And that's going to be true for any log function. Let's just do it in general. Y equals log base b of x. Right? We have b to the y equals x. And when y is 0, x equals 1. And that's true for any base. So 1 comma 0 will be on any log graph. Well, they'll be on any log graph, on all log graphs, right? Without a transformation, right? Without transformations. So that's kind of the point I use to orient myself for a log function. All right, I know without transformations, it's going to pass through the point 1 comma 0. So if I look at the multiple choice answers here, this will be shifting left 2, right, and down 1. So if I take this point and I move it left 2 and down 1, I'm going to end up over here. And that's not a point on my graph, so clearly it's not choice 1. Right, this is telling us to move 3 to the right and up 1. So if I go 3 to the right and up 1 from my point 1 comma 0, 1, 2, 3, and up 1, I'm going to end up there, which again is not a point on my graph. So I know it's not choice 2. And then for 3 and 4, we're moving left 3 and down 1. So if I move left 3 and down 1, I end up at this point. And that's on both of them, so these are both potentially correct answers. So the only thing that's different about these two is the base, right? Or how fast, or how slowly rather, it's increasing, right? So really the best way is to just take a point and plug it in and see what happens. So for example, if I take the point 1, 2, 3, 4, 5, I'm going to try plugging in this point 5, 2, and seeing which equation fulfills or satisfies that point. So 5, 2, that means 2 equals, using choice 3, 2 equals log base 2 of 5 plus 3 minus 1. Alright, so let's solve this log equation. We haven't talked about this, but same way you can solve any other equation. We're not actually solving the equation, we're just seeing if they're equivalent. But if I add 1 to both sides, I should put a question mark above the equal, I get 3. Does 3 equal log base 2 of 8? And yes, it does, because if I put this in exponential form, I get 2 cubed is equal to 8, right? And 2 cubed does equal 8, that does satisfy it. Right, if you just think about log base 2 of 8, 2 to the what power is equal to 8, 2 to the third power is 8, 3 equals 3. Right, it checks out. So that is the correct answer. If you try plugging in for choice 4, we're going to have the same thing except log base 3. Right, and 3 to the third power is not 8. Right, log base 3 of 8 is not 3. So that's it for that one. And let's just answer some basic questions. What is the x-intercept, the y-intercept, domain, and range? So for any function always, when we're looking for the x-intercept, we're looking for when the function is equal to 0. When does f of x equal 0? Right? When does it cross the x-axis? Which is always something, comma, 0. The y value 0. So 0 equals log base 2 of 3x minus 4. If I change this to exponential form, 2 to the 0 power equals 3x minus 4. Again, what power function, what power of 2 is equal to 3x minus 4? The power being what it's equal to here, which is 0. So 1 equals 3x minus 4. 5 equals 3x. X is 5/3. Alright, so the x-intercept will be 5 over 3, comma, 0. Alright, next find the y-intercept. The y-intercept is going to happen when x is 0. Right? When x equals 0. So let's plug in a 0. F of 0 is going to equal log base 2 of 3 times 0, which is 0, or log base 2 of negative 4. So what is log base 2 of negative 4? In other words, 2 to the what power, I'm going to use a y for the what power. 2 to the what power is equal to negative 4. There is no value of y, right? Can we raise 2 to any exponent and get a negative value? No, it's impossible, right? So there is no value for y. In other words, there is no y-intercept. There is no y-intercept. And this should make sense because if we look at our log graphs, right, none of them had a y-intercept. The domain was x is greater than 0, right, without any transformations. So if we're not shifting it to the left, right, it's not going to have a y-intercept, right? And this one, we have a shift to the right. Right, the shift right is not 4 units, by the way, right? It's going to be 3 times x minus 4/3. It's a shift to the right 4/3 unit. So what is the domain? Right, to get the domain, well, we know that log base b of x, we know the domain for a general log function like this is that x has to be greater than 0. Right? And that is because we cannot take the log of 0 or a log of a negative number. Right? We talked about that yesterday. Make sure that makes sense. So for this function, which is y equals log base 2 of 3x minus 4. Kind of like with square root functions, you can't have a negative under the square root. For a log function, you can't take the log of 0 or a negative number. So what we do to get the domain is all we have to do is take this argument, right, what we're taking the log of, 3x minus 4, and we set that to be greater than 0. Because we can only take the log of positive values of numbers greater than 0. So when we solve for this, we get 3x is greater than 4, x is greater than 4/3, and that's our domain. Right, and if you want to check on your calculator, feel free to graph it. You will see that is the domain. Or that is where our vertical asymptote is also, at 4/3. And what's the range? So for any log graph, right, our domain is going to be all real numbers. Right, y is the element of the reals, all real numbers, negative infinity to infinity. If I go back to the warm-up, right, no matter how slowly it looks like it's growing, right, this is not a horizontal asymptote. There's no horizontal asymptote here. This is always increasing, just increasing really, really, really slowly, like we talked about. All right, so that's going to be it for log graphs. There's not too much graphing of logs, but I do want you to understand them still and see that the transformations still apply. So there are two special logarithms. This is going to be a quick section, I think. So while the base of a logarithm can have many different values, there are two bases that are used more often than others. So when I talk about the base, right, I'm talking about this guy over here. So one of the special logs is called the common log, and that is when the base is equal to 10. All right, this is so special, in fact, that when I write log of x without a base, it is implied that it is base 10. All right? This means that there's really a 10 there, but we don't need to write it. It's like when we write square root of 4. We don't need to write this 2 because when we write square root, we know it's the square root, right? It's the second f root of 4. So, yeah, so that's it. This implies that there's a 10 here. All right, this means the base is 10. So log x just really means log base 10 of x. All right, and the other very special log that we'll use quite often is base e. Do you guys remember e? Euler's number, right? We saw that when we were compounding continuously. So actually a lot of things grow continuously in the real world. Like the size of a vegetable, like cauliflower, right? It's growing continuously. So that's going to have some factor e involved. So this e shows up all the time. Again, this is Euler's number, which is approximately 2.718 something, something, something. So when you have log base e, the way we're going to write this is like this, ln of x. Right? ln, we call this the natural log, right? Which is the opposite of this guy. There should have been an x there. I guess it got reversed, what was in front. So it's the opposite of that. We got the natural log ln of x. So ln of x, that's the way you say it. You say ln of x. Why did I put parentheses? Or maybe I should write it like this. ln of x is how you would say it. Or you can say the natural log of x. Right? That has more syllables though, so I say ln of x. Right? Don't say ln. Ln is not a thing. Or maybe it is, but it's not a thing for me. So anyway, common logarithm, to summarize, which is pretty much the same thing up there, but common log has a base of 10. with a regular notation, we would write it like log base 10 of x, right? But no one is ever going to write this, just like you do not write the 2 when you take a square root of something, right? The way people are going to write this is just log x, all right? And when our base is e, that'll of course be log base e of x, but again, no one writes this. People write the natural log, or ln of x. All right? So first take a guess, approximate each answer, then use your calculator to evaluate the following. See if the answers make sense to you. So this is just a little check to see if you have like some basic intuition about what logs are. So what do you think log of 3,000 is going to equal? Also, I don't have a calculator with me, so I'm just going to guess first. That's because I'm hiding in the bathroom where it's the quietest. But hold on, let me get out of here and let me go access a calculator. Alright, so log of 3,000. So getting my calculator, I'm going to approximate first without a calculator. What's log of 3,000? So remember, I don't have a base here, which means the base is really 10. So I'm thinking 10 to the what power is equal to 3,000. Well, I know that 10 cubed is equal to 1,000. And I know that 10 to the 4th is equal to 10,000. So if I had a guess, well, I know the value has to be in between 3 and 4. And you might guess, well, it's closer to 1,000, so it should be less than a half. But when things grow exponentially, that's not the way it works. So if I had to approximate this, I would guess around 3.5. All right. I'm going to check on my calculator at the end. I actually do not know the values. I'm just approximating, as you should be. All right, so why don't you guys approximate B and C also? All right, but for B, this is 10 to some power. I'm going to use y again, is equal to 2. So I know 10 to the 0 power is equal to 1, and 10 to the first power equals 10. So I know this is in between 0 and 1. So would it be to the half power is the square root of 10 2? No, square root of 10 has to be more than 2, right? Because 3 times 3. So I'm going to say maybe this is about, I don't know, 0.3. That's my guess. But as long as you have a number between 0 and 1, I'd be happy for your guess. Right? And thus we have a base of pi, right? Pi is a number. It's just pi to the what power equals 100. 3.1415 approximately to the what power is 100. I don't know. 3 cubed is 27. 3 to the 4th is 81. So maybe around pi to the 4th is going to be 100. So I'm going to guess around 4. So, actually, all right, let's get a calculator. Hold on. Okay. Yeah, and the log button, you'll see it next to the number 1. So if you hit Control, that button next to the number 1, you'll have log. So your calculator is really nice because you can do different bases. When I went to high school a long time ago, I could only do log base 10. But if you don't fill in the base, it'll automatically default to log base 10, or the common log, so you don't have to fill it in. And whoa, I was really close. This is actually about 3.477. Alright, so you should be able to kind of approximate these log values. Log base 2, that is 0.30103. Right, something, something, something. And log pi button is next to the letter H. Base 100. Sorry, log base pi of 100 is All right, so 0.2293. Wow, that was okay. Guys probably won't believe me when I tell you I did this without a calculator, but yeah, so those are the actual values. Happen to be close to my approximations, but I was just guessing. And so this answered the following without using your calculator, and then you can check on your calculator after if you want. But these will have exact values. And normally I do like a quick exit ticket in class, no calculator, where you have to just calculate some log or natural log values. But can't really do a no calculator quiz at home or when you guys are at home, so I'll just show you how to do these. So ln of e, right? This means e to the what power. If I make this equal to y, e to the y power equals e, right? The base is e. E to the what power is equal to e. Well, I know e to the first power is equal to e, so ln of e equals 1. All right, log of 1,000. There's no base. That means this is the common log, which means the base is 10. That means 10 to the what power is equal to 1,000. 10 to the third power is equal to 1,000. This is equal to 3. All right, e, again, when there's nothing it's equal to, I just make it equal to y. Right, so e to the y equals e to the fifth. What's y? Y is 5. Hopefully that makes sense. Right, e to the fifth equals e to the fifth. E to the what power equals the square root of e cubed. So square root of e cubed, writing that with rational exponents, that's 3 halves. So y is 3 halves, or all of this is equal to 3 halves. Right, and sorry. And if you want, you can type this into your calculator to check. All right, moving on. E to the what power is equal to 0. Can that be done? No, it cannot be done. So let me check on the calculator. If you type in natural log, that's next to the log button on your calculator, by the way. Right, if you type in ln of 0, you get undefined. Alright, same idea here. E to the what power is going to equal e to the negative second. That's 1 over e squared. So that is negative 2. And e to the what power is 1. Anything to the 0 power is 1. Alright, so that's that. Today we covered the special logs, the common log, and the natural log. And did some basic transformations. So see you guys next time. Any questions, as always, just send me a message. And take care. Stay safe. Bye-bye.